Why is space travel hard? Why does it cost between $5,000 and $10,000 per pound to launch something into space? Today I'm going to help you answer that question, or at least get a good start at answering it, by telling you about the ideal rocket equation. So last time we talked about the basics of rocket propulsion, which is the process by which rockets produce thrust and lift off to fly through the atmosphere and into space. If you didn't watch last time's video, check it out right here. So today we're going to be talking about the ideal rocket equation, also known as the Tsiolkovsky rocket equation, named after the boy Konstantin Tsiolkovsky, who came up with the equation in the early 20th century. Now this equation is pretty important, and the reason is because it helps us calculate the maximum change in velocity that a rocket can achieve based on some of its characteristics. Now essentially what that means is, what is the maximum speed that your rocket can reach? And so the farther away you want to go from Earth, the greater change in velocity you'll need. But believe it or not, the hardest part is actually getting out of Earth's atmosphere. In fact, it takes about half of the change in velocity needed to reach all the way to Mars just to get out of Earth's atmosphere and into low Earth orbit. So what is this magical equation? Now you're probably like, whoa, what is that? But before we dive in, let's just define a few variables. So that maximum change in velocity that we talked about is the delta V term in the equation. V sub E refers to the exhaust velocity, which is how fast the exhaust gas is shooting out of the nozzle, if you remember from last time. Now the exhaust velocity is multiplied by the natural logarithm of the initial mass divided by the final mass of the rocket. So the initial mass of the rocket is the rocket loaded, on the launch pad ready to go with all of the propellant, the fuel and the oxidizer, the actual structure of the rocket, so all of the metal and all of the electronics, the payload, which is what the rocket is taking into space, and a crew, if there is one. Now the final mass of the rocket is the same as the initial mass, except for one key thing. There's no propellant. And that's because the final mass refers to after all of the propellant has been exhausted. So the maximum change in velocity of the rocket is equal to the exhaust velocity multiplied by the natural logarithm of the mass of the rocket with the propellant, which is the initial mass, divided by the mass of the rocket without the propellant, which is the final mass. Now, I get that this equation may seem confusing, and it kind of is, but let's see why it actually makes sense. So the exhaust velocity refers to how fast all of that hot exhaust gas is being pushed out of the nozzle. A higher velocity gives you more thrust or more force, which in turn allows the rocket to have a higher acceleration and reach a greater maximum velocity. What's up with this whole natural log of the masses thing? So you don't need to worry about the natural logarithm if you don't know what it is, because it's just a function. What you need to know is that the greater the rocket's initial mass is compared to its final mass, the larger the percentage of the rocket's initial mass is just propellant. The greater this fraction is, and the greater maximum change in velocity is that you can achieve. So to recap, increasing the exhaust velocity of the rocket, or increasing the percentage of the rocket's total mass that is just propellant, increases the maximum change in velocity that your rocket can achieve. So we talked about calculating the maximum change in velocity that a rocket can achieve and how far it can go. But what about the other way around? We can also use this equation to determine the amount of propellant that we need for our rocket to be able to achieve a certain change in velocity and reach a certain destination. Basically, if we know where we want to go, we know the maximum change in velocity that our rocket needs in order to reach there. We can also determine the exhaust velocity based on the type of propellant that we use. Remember that a propellant consists of a fuel and an oxidizer, which react together and shoot out of the nozzle, providing that force of thrust which allows the rocket to lift upwards. Now the exhaust velocity depends on the combination of fuel and oxidizer that we use, because some combinations are more energetic when they combust than others. For example, one of the most energetic combinations that we know of is a fuel of liquid hydrogen and an oxidizer of liquid oxygen. Now this combination specifically gives us an exhaust velocity of about 4.4 kilometers per second, which is almost 10,000 miles an hour, so really fast. If we know where we want to go, we know the maximum change in velocity that we need to get there. We also know the exhaust velocity given the propellants that we use, so we can put these two values into the equation and get the ratio between the initial and final masses, which we can use to tell us how much of the rocket's initial mass is just propellant. And we'll see why that's important later on. Unfortunately, while the rocket equation is very helpful, it constantly reminds us of our current limitations. So for example, let's say you're an astronaut and you want to go to the International Space Station for those killer views. So the ISS is located about 254 miles or 400 kilometers above Earth in something we call low Earth orbit. The International Space Station is the largest man-made structure in space, and it's where the space shuttle went for its missions. So in order to get into the same orbit as the International Space Station, you need your maximum change in velocity to be about 8 kilometers per second, which is about 18,000 miles an hour, or almost 300 times faster than a car on the highway. So we have our rocket's required velocity. Let's talk about our exhaust velocity. Again, the exhaust velocity is determined by the propellant, so you're like, okay, let's use hydrogen and oxygen like we talked about earlier. So like I mentioned, the combustion of hydrogen and oxygen provides you with a certain amount of energy, and so the maximum exhaust velocity that you can achieve is approximately 4.4 kilometers per second, which is almost 10,000 miles an hour. So that sounds pretty good. We can put in our maximum change in velocity and our exhaust velocity into the ideal rocket equation in order to find out the proportion between the initial mass and the final mass. Now, once again, we can use this proportion to tell us the percentage of the rocket's initial mass that is just made up of propellant. So before I say anything, why don't you guys guess what you think this percentage is? So how much of the rocket's initial mass is just the fuel and the oxidizer? So keep in mind that this is just the percentage of the fuel and the oxidizer compared to the fuel and oxidizer plus the entire structure of the rocket, all of the engines, the payload, the crew, the electrical components, everything. So what'd you say? 20%? 30%? Maybe even 50%? Well, to give you some reference, your car's percentage of propellant is approximately 5%, and we're talking about the fuel here. For an airplane, it might be between 30 and 50%. For a lot of explosive devices, it might be a little bit over 50%. So what do you think the percentage of propellant is for a rocket? It turns out that the propellant usually makes up between 85 and 90% of the rocket's total mass when it's sitting on the launch pad. 85 to 90%, which means that for everything else, the actual structure of what you think is the rocket, the engines, the payload, the people on the rocket, only makes up 10 to 15% of the total mass, which is pretty mind-blowing. Now the problem here is that you have so much propellant that there's barely any room for anything else, like for if you need a payload which you're taking up to space. So rockets are always constrained by the amount of propellant that they need in order to achieve this maximum change in velocity, which makes engineering these rockets extremely difficult. And this leads us to probably the biggest takeaway of the video today. Why is space travel so hard, and why is it so expensive? Of course, there are many reasons for this, but the rocket equation does give us one. The farther we want to go, the greater maximum change in velocity that the rocket needs. However, this propellant ends up taking up such a large percentage of the rocket's mass, and at some point it'll be impossible to travel further because we won't be able to make our rocket's structure light enough and strong enough, or even carry a meaningful payload up into space. Additionally, there's a snowball effect, where adding more propellant increases the total mass of the rocket, so you need more propellant to carry that propellant to lift the rocket up into space. And it just keeps compounding. So today, engineers have to push the boundaries and continue to push the boundaries of science and technology in terms of making rockets as light as possible and as strong as possible, and increasing the efficiency of propulsion systems. Of course, all of this requires a lot of money, so building a rocket and launching a rocket is an extremely expensive process. And that brings us to the end of today's video. If you want to learn more about the implications of the rocket equation, let me know down in the comments below. Thank you so much for watching, and I hope you guys learned something today. If you enjoyed the video, please consider giving it a like and subscribing down below. And feel free to put any questions or comments you have in the comment section, and I'll do my best to answer them. Thanks again, and see you guys soon.